to say is problem 222 is everything that we just did. Well, it's set for, oh yeah, let me set this up a tiny bit. Okay, problem 222. All right, what it does, it's the same idea. It's set for what we're given is the psi total of x at t equals 0, right? So instead of it being, you know, minus a to plus a, like that example problem, it's given as this. So what is that shape that you guys recognize? It's a Gaussian. All right, so they give this as a Gaussian. The time equals 0. This is a Gaussian. So this has the form of e to the minus x minus x0 squared over 2 times sigma, where sigma is the standard deviation, right?
That's a psi total.
That's psi total at time equals 0. So this is just like the example problem, but at time equals 0, it looks like a Gaussian. So then, how do you find the probability amplitudes? You do the Fourier integral. So what you do is you come all the way over into here, over into here. Oh crap, I erased it. But now you know that psi of k equals 1 over 2 pi, the integral from minus infinity to plus infinity, a psi of x in comma 0, e to the minus I kx dx, right? Now you guys should be able to write it down without ever having to do anything. So you plug this into there, all right? And when you do all this, let me just tell you that the answer is that psi of k equals Gaussian as well. What's that?
5k.
5k. Thank you. 5k is Gaussian. Yeah, please do. So 5k comes out to be Gaussian as well.
Be all
Right?
video.
Now, so all the machinery is the same and turn the crank and everything, but the only thing that I want to point out is that the Gaussian initial wave packet that you start out with is called the minimal uncertainty wave function. So in other words, the particles you describe with Gaussians at t equals 0, they will give you your k-space representation that when you combine with your x-space representation gives you the minimum uncertainty that you can have. So in other words, it's the most precise wave packet you can describe.
So instead of it equals each curve.
Yeah, so within the Heisenberg uncertainty principle, this is the best you can do about describing particles. So almost everywhere, particles are described as Gaussian wave packets.
Phi of k is Gaussian also, but it's called a minimal what?
It's the minimal uncertainty wave packet. So when you solve for the Gaussian, you throw it back in, you get a total wave packet, and that total wave packet's x and k-space representation gives you the smallest amount of uncertainty you can have in position and momentum. Yes? Okay, so that's just for that homework. I want to get to the last thing that won't take me long at all right? It'll take you 2 minutes, so much, maybe afterwards, all right?
Can you repeat that thing about being the smallest? That's right, just that last sentence you said. When you throw, when you have the x and k representation,
Yeah, so when I initially say that my initial particle is in a Gaussian, and then I solve for essentially the envelope, and then I solve for the whole wave packet back here, that wave packet in both the x space and the k space will be the situation where I have the least amount of uncertainty in my position in momentum. So it's the best you can do. Look, are we confined to the uncertainty principle?
Yes.
Yeah. Aren't you curious what's the best functions that will give you? So what is the function that will give you the equal to instead of the greater than?
Yeah.
It's the Gaussian. All right. Yep.
It would be helpful to have the weekend in order to then come in on Tuesday do a test.
Okay, no, the test is Thursday.
Okay,
All right, we talked about things at the beginning of class.
yeah, no.
Yeah, so, all right, so let's go on. All right, the next question, and this is what's done in Harris, okay? And what to do is this, is look, let's look at the probability density of these things. All right? And so what I'm going to do, and this is done in Harris, and I'm just going to write down the result, but it shouldn't seem too wacky. Psi total or psi general of x and t squared is equal to, you ready? C squared, all divided by the square root of 1 plus d squared times t squared, all divided by epsilon squared. Epsilon of 4 epsilon to the 4th, all times e to the minus x minus st quantity squared, all divided by 2 epsilon squared times 1 plus d squared t squared, all divided by 4 epsilon to the 4th. Okay? So what is this, guys? Tell me, what is this? It's just this thing, right? Squared. All right? Okay, where s equals d omega dk, evaluate at k naught. So this is what Griff has called omega naught prime, right? And d equals d squared omega dk squared. K naught. Okay, so let's plot this up. Can anybody tell me what this function looks like?
What variable is that? Yeah.
Everything else is a constant. The only variables you have are x and t.
It's before the t goes, except t.
Did c e to this thing? So you guys should be able to see the functional form. This is an amplitude,
Yeah.
right? And then this is, what does this look like? I just wrote it down over here. E to the minus
Yeah, it's a
x
Gaussian.
minus x naught squared, all divided by 2 sigma squared.
Isn't that what you call it?
Gaussian.
It's a Gaussian. This is a Gaussian weighted by some amplitude. Right? This is an amplitude. Okay, so look, it looks like this. So now this is x, and here's my Gaussian. Okay, so this amplitude over here, this amplitude is a function of 1 over the square root of 1 plus d squared t squared. All right, and then the other thing to notice is, look, what is this width right here? This width is 2 epsilon squared times this crap.
Which is the 2 sigma.
Right, so this is the 2 epsilon squared times 1 plus d squared t squared over 4 epsilon to the 4th. All right?
So the sigma is the standard deviation, so that's just...
So this is all, this whole term down here is like the standard deviation.
Yeah.
All right, and then this is the amplitude. Okay, so for our case, we had omega equals h bar k squared over 2m, right? Everybody agree? That's what we had for our... Okay, and then we also had that we had s, equals omega naught prime equals what? K over 2m, hk over 2m.
Oh, they're H bars, right?
H bar, yeah, which equals the group velocity. All right, and now here's the thing: do we have a d?
Well, S is h bar k over m, not 2m.
All right,
no,
because
no,
that's
yeah,
square.
very good. All right, but do we have a d in this case? A d is the second derivative with respect to k.
H bar over m.
So this comes out to be h bar over m. Now, because we have an h bar over m, let's say d equals 0. Let's say that there was no d right here. What does this amplitude become?
1.
1. And what happens to this full width at half max? as a function of time?
2 epsilon squared.
Okay, it's constant. But if I have a second derivative down here, what does it mean about my amplitude as time goes on?
It's higher and higher.
It's
Lower.
It gets smaller and smaller. And what happens to my width as time goes on?
It's
Bigger.
Thinner? Thicker. It gets
How
bigger.
big?
yeah,
Shorter.
it flattens and spreads
So what
out.
happens is that as time goes on, this wave packet becomes, all right, so this is psi squared at t equals 0, and this is psi squared at t greater than 0. And so what's happening to our particle?
It's like a mound of jello or clay or
Our particle that we initially had right here, as time goes on, what's happening to it?
It's more and more uncertain.
Its probability started to spread out as a function of time, and that's called dispersion.
How could D ever be 0? Good,
If you look at like just a plane wave, like if you just had like a plane wave, then you would have a non-zero answer right here. So
if D is the
look,
second derivative.
you have to say where does omega come from? Omega comes from psi double squared plus well, here's what you do. You got to start out with minus h bar squared over 2m psi double star plus ep times psi, or b, you're saying b in here, but b times psi equals e times psi, right? So then what you do is you end up with psi double prime plus, minus 2m over h bar squared. Let's make a plus, then e minus b times psi equals 0. And so this is where k comes from. K essentially equals the square root of 2m e minus b over h bar squared. All right? And so what we found for the free particle, that this thing came out to be k squared. Well, I forget how we got it, but maybe it may.
It's just that this is not a test, is it?
No, this is not in the test. All right, and so when we found it is this relationship that we got, the omega equals this thing squared. So how does it equal that thing squared? How can I make that inversely related?
Your classical
Well, if you plug that in for
representation
K.
of A and B.
Yeah, I forgot where I got it. All right, I forgot how to get it. But in any case, what we did, we got this for a free particle, and this free particle came from here. The way you can have a case where you have a K that is not, where you have a dispersion that is equal to 0, is to have a different relationship between the energy and the potential.
Oh, that's right.
For the potential, what we had is V equals 0. All right? And so that's where we got that dispersion. So the whole dispersion relationship comes from the energy and the potential. And for our case, we did a free particle. So in other words, here's what you say, is this relationship, omega equals h bar over k, is called the free particle dispersion relation. And the reason why it's called the dispersion relationship is, one, its first derivative we found out is the group velocity. And two, its second derivative tells you how that wave function probability density disperses as a function of time. Okay, so let me just see if I can clear up where my k came from. Oh, okay. Let's see.
It's like because we have omega, and it's h bar omega. That's the energy.
Yeah, so over here, what happens is I have V equals 0.
We have an h bar omega for E, right?
Yeah, it's equation 291, all right? 291, which is what we did for the free particle, all right?
So, what will be on the test?
I already said, so if everybody who was here on time knows what's going to be on the test, I have to say. All right?
Just this.
Just this? No.
Stuff he's done on the board.
Well, you guys can talk about it, I'm not going to
So
talk
any
about it.
questions